Hello everyone, I'm Kamal Utala. I'm a pre-final year student at IIT Roorkee pursuing BTech in Engineering Physics. Today I will be presenting on the experiment which deals with light dependent resistors. So what is the objective of this experiment? Well, the main objective of this experiment is to study the characteristics of an LDR, that is the light dependent resistor. Also to plot the VI curves of the LDR at different intensities of light. So let us dive into the theory of this first of all. So as you can see, there is this red lining over here. So this is the main photosensitive material of the LDR. This is the place where the action happens in the LDR. So this photosensitive material is basically a semiconducting material. So consider a semiconducting material. This is the valence band, this is the conduction band, and this is the forbidden energy gap. So if it is a direct band gap semiconductor, so as soon as we shine light onto it, we know that the electrons in the valence band will be excited to the conduction band. So we'll have an abundance of free electrons in the conduction band, and also as the electrons excite from the valence band, they leave behind the holes. So the abundance of holes in the valence band also increases. Basically what happens is, we know that sigma is n times mu q times plus q times p of mu. So we are basically increasing n and p in the semiconductor, so because of which there is an increase in the conductivity of the semiconductor. So there is a change in semiconductor's conductivity, which can be manifested as a change in voltage if we use an external power source. So using this we can study the characteristics of the LDR. What all we need for this? So we need a variable DC voltage supplies. In our case it is from 0 to 3 volts, and we need an ammeter to measure current. We need an LDR itself, of course, it's the main component. We need some connecting wires, and also we need a light source. Consider the schematic over here. So this is the LDR, this is the circuit symbol for LDR, and we are using a source of light and shining it onto the LDR. And now there is this variable DC voltage supplier. As we vary this, we will see that the current will also be changing. So what we'll be doing in the experiment is to change the voltage and simultaneously measure the current while the intensity is constant. So at a constant intensity, we'll be studying the VI characteristics of the LDR. Coming to the procedure, you can see that the LDR is present over here, and you have to take markings from the LDR at some fixed distances. In my case, I took 4 centimeters, 6 centimeters, and 8 centimeters. The idea is very simple. The LDR is over here, and as you move the source farther away from the LDR, the intensity of light will be changing. We know that I is equals to P by A. So the P will be constant for the given flashlight or any power source that you are using. So as you increase the distance, the effective area that is being covered by the power source will be increasing. So with an increase in distance, the area will also be increasing, as you can see here. So the intensity will be decreasing. So as we increase the distance, the area is increasing and the intensity is decreasing. So basically the intensity at 4 will be greater than intensity at 6 will be greater than intensity at 8. So we will be studying the LDR characteristics at 3 different intensities. Consider the module. So we can see that there is a knob over here which is basically to control the voltage. The display of voltage can be seen on the left screen, and the right screen shows the display of current. We can see that when the LDR is not shown by a light, the current was not changing. As you can see, even though we were changing the voltage, there was no change in the current. That is because the LDR right now, the LDR is in dark. There is no source of light for it, so it has a very high resistance. So because of its high resistance, even though there is a change in V, the current is not changing, because I and R are inversely proportional. So because the resistance is quite high, the change in current is negligible, as we can see in this case. So now let us take a light source. As we can see, we are using the flashlight from a mobile phone, and we are shining it onto the LDR. We'll keep the mobile phone at the markings that were taken by us before. So keeping the phone at a marking, in this case I am keeping it at x is equals to 4 centimeters, and I am taking the measurements. So you can see that as I am rotating the knob, that is increasing the voltage. Now we can see that there is an increase in the current, because we started to shine the LDR with a light, and in this case the resistance has decreased, because of which we can see a change in current with the change in voltage. In this clip you can see that as I am decreasing the intensity, that is by taking the phone farther away from the LDR and decreasing the intensity, we can see that at the given voltage the value of current is decreasing. It has come down from 0.6 to 0.3. So when the intensity is decreasing, the current is also decreasing at a given voltage. So at all the 3 distances, we will take the readings of V and I, and we will plot them. So this is the result that we have got. We have constantly changed the voltage by an amount of 0.4 units, and we have recorded the current measurements accordingly at x equals to 4, 6 and 8. So at 0 voltage we can see that the current is 0, and accordingly the current is increasing with the voltage increase. Let us plot these and analyze what is happening. So as you can see, x is equals to 4 is represented by this graph. So we can see that the slope of x equals to 4 is greater than the slope of x equals to 6 is greater than the slope of x equals to 8. The slope of the IV graph basically gives you a measure of the conductivity, because I is equals to G times V, where G is the conductance. So we can see that at x equals to 4 we have a greater slope. That means sigma at 4 centimeters is greater than sigma at 6 centimeters is greater than sigma at 8 centimeters. So our experimental observations are holding with the theoretical model that we had discussed before, that with an increase in the intensity, the conductance is also increasing. And we can also see that The LDR is an ohmic resistance because the IV curve is a linear plot. So as V and I are linearly related, we can very easily say that it's an ohmic resistance, and it shows a linear behavior in I and V. Thank you for listening.